Hello, fellow Voyagers, and welcome to the Night Voyager. This is actually our very first cosmic journey together, and I couldn't be more excited to share it with you. I'm starting this channel because I believe there's something magical about exploring the universe as we drift towards sleep. And speaking of Voyagers, we couldn't have chosen a more perfect topic for our inaugural episode. The Night Voyager exploring the actual Voyagers. It feels like destiny, doesn't it? Before we start, I'd love to know where you're joining me from and invite you to share one word that captures how you're feeling right now. Maybe it's peaceful, it's curious, or grateful. And if these gentle cosmic tales help you find peace in your evenings, please consider subscribing to join our growing community of night sky dreamers. And please let me know if there's any science topic that you would like me to cover in upcoming videos. Tonight we're embarking on something truly special, a story that spans generations and reaches farther into space than any other human-made objects in history. We're going to explore the incredible journey of Voyager 1 and Voyager 2, twin spacecraft that have become our cosmic ambassadors to the stars. These remarkable machines, launched in 1977 when Star Wars first hit theaters and disco was still king, are still sending us messages from the edge of known space. This isn't just a story about technology or space exploration. It's a deeply human tale about our collective desire to reach beyond our horizons. Imagine sending a message in a bottle, except this bottle is traveling at nearly 40,000 miles per hour and carries the sounds, music, and greetings from Earth on golden records that will outlast our civilization. These records, curated by Carl Sagan and his team, are like cosmic time capsules, carrying whale songs, Chuck Berry's Johnny B. Good, and greetings in 55 languages into the infinite darkness. We'll journey alongside these intrepid explorers as they reveal the volcanic fury of Jupiter's moon Io, discover the potential ocean worlds of Europa and Enceladus, and listen to the ethereal songs of Saturn's rings. We'll marvel at how these car-sized spacecraft, built with computing power less sophisticated than a modern digital watch, continue to operate after nearly half a century in the harshest environment imaginable. We'll also contemplate the famous pale blue dot photograph, where Voyager 1 showed us our entire world as nothing more than a tiny speck of light in the cosmic ocean. It's a perspective that changed how we see ourselves in the universe, making us realize just how precious and unique our small blue world truly is. As we begin this journey together, imagine something remarkable happening right at this very moment. While you're listening to these words, both Voyagers are pushing through the boundary of our solar system, carrying humanity's message into interstellar space. They'll continue their silent journey long after we're gone, perhaps becoming humanity's longest-lasting legacy among the stars. The Voyager twins have journeyed so far that their radio signals, traveling at the speed of light itself, take over 22 hours to reach our planet. To put this mind-bending distance into perspective, if you could somehow drive to where Voyager 1 is currently located at highway speeds, say 70 miles per hour, the journey would take you approximately 17 million years. That's longer than humans have existed as a species. These spacecraft continue communicating with us, using transmitters no more powerful than the light bulb in your refrigerator. Think about the magnitude of this challenge. It's like trying to hear someone whisper your name from the next state over, while you're standing next to a thundering waterfall. Yet somehow, through the cosmic static and interference, our deep space network manages to catch these faint whispers from the void. The Voyagers have entered what scientists call interstellar space, that vast ocean between the stars where our sun's influence finally gives way to the forces of the galaxy itself. Think of our solar system like a massive ship sailing through space, with the sun's magnetic field and solar wind creating a protective bow wave called the heliosphere. This cosmic bubble shields us from much of the galaxy's radiation, creating a relatively safe harbor for life to flourish. The Voyagers have now pushed through this protective boundary into the true cosmic deep, a realm where the environment is fundamentally different from anything within our solar neighborhood. To help you visualize just how far they've traveled, imagine scaling our entire solar system down to the size of the United States. In this cosmic miniature, The Sun would sit in New York City, Mars would be somewhere around Ohio, Jupiter near Colorado, and distant Pluto would rest near Los Angeles. At this scale, the Voyagers would now be floating somewhere far out in the Pacific Ocean, still moving away from our miniature continent at a steady pace, still sending back their faint signals across that vast expanse. What's truly mind-bending is the timeline we're dealing with. These spacecraft will likely outlast not just our current civilization, but Earth itself. Billions of years from now, when our sun swells into a red giant and boils away Earth's oceans, when all traces of human civilization have long since vanished, the Voyagers will still be sailing through the Milky Way galaxy. They're carrying those golden records, humanity's greatest hits album, into a future so distant that it challenges our ability to comprehend time itself. The most remarkable aspect of this cosmic odyssey might be the technology that makes it possible. These incredible machines were built with electronics less sophisticated than what you'll find in a modern microwave oven. Their onboard computers possess about 235,000 times less memory than a contemporary smartphone, yet they've managed to revolutionize our understanding of the solar system and continue making groundbreaking discoveries even today. Let me walk you through the engineering marvel that is a Voyager spacecraft. Each one weighs about 1,820 pounds, roughly the same as a small car. But unlike any earthly vehicle, these cosmic travelers have each journeyed over 12 billion miles. That's equivalent to driving around Earth's equator nearly 500,000 times, or making more than 25,000 round trips to the Moon. At the heart of each spacecraft lies a computer system that represents a fascinating time capsule of 1970s technology. The main computer has just 4,096 words of memory. You could store its entire memory capacity in a text file smaller than a typical email. Yet this tiny electronic brain manages all spacecraft functions, from maintaining precise orientation to formatting scientific data for transmission across billions of miles of space. The power system is equally remarkable. Each Voyager runs on what's called a radioisotope thermoelectric generator, or RTG. Think of it as a nuclear battery that converts heat from radioactive plutonium decay directly into electricity. It's the same principle you experience when you touch a metal spoon that's been sitting in hot coffee and feel the handle warm up. The Seebeck effect, where a temperature difference creates electrical current. These cosmic power plants started their journey producing about 470 watts of electricity, but plutonium-238 decays predictably over time, losing about 4 watts each year, so by now they're operating on roughly 220 watts, less power than most household vacuum cleaners. This declining power creates one of the mission's most poignant ongoing dramas. Every few years, engineers must make heartbreaking decisions about which instruments to keep running and which to shut down forever. It's like slowly dimming the lights in a house while trying to keep the most important rooms functional. Some instruments that revealed the magnificent secrets of Jupiter and Saturn decades ago now sleep eternally, their power redirected to the sensors that are writing humanity's first dispatches from interstellar space. The precision required for their navigation boggles the mind. Consider the challenge of pointing Voyager's dish antenna toward Earth. The spacecraft moves at 38,000 miles per hour, while Earth spins at 1,000 miles per hour at the equator and orbits the Sun at 67,000 miles per hour. Meanwhile, our entire solar system races through the galaxy at 514,000 miles per hour. It's like trying to keep a laser pointer aimed at a specific moving target while you're also moving, and everything else is moving, all in different directions, across distances measured in billions of miles. The scientific foundation underlying the Voyager missions represents one of humanity's greatest intellectual achievements. When these spacecraft launched in 1977, we knew embarrassingly little about the outer solar system. Jupiter was a mysterious giant with a handful of known moons. Saturn's rings were thought to be simple, uniform structures. Uranus and Neptune remained almost complete mysteries, known primarily as distant points of light in our telescopes. The Voyagers changed everything. At Jupiter, they discovered that what we thought was a peaceful gas giant was actually a roiling, dynamic world of incredible complexity. The Great Red Spot, visible from Earth as a simple oval feature, revealed itself to be a hurricane larger than our entire planet, with winds exceeding 400 miles per hour and a structure so complex that we're still analyzing the data today. But perhaps the most shocking discovery was Io, Jupiter's innermost large moon. Scientists expected a cold, dead world, pockmarked with ancient craters like our own moon. Instead, Voyager 1 revealed a hellscape of active volcanoes, spewing sulfur and sulfur dioxide hundreds of miles into space. It was like discovering that what you thought was a frozen wasteland was actually a world more geologically active than Earth. These volcanic eruptions are driven by tidal forces. Jupiter's immense gravity literally kneads Io's interior like bread dough, generating enough heat to melt rock and power the most dramatic volcanism in the solar system. Imagine being the first human being to see these images come back from space. Linda Morabito, a young engineer at JPL, was the one who first spotted that strange plume rising from Io's surface. She was just doing routine navigation work when she noticed something that shouldn't have been there. In that moment, she became the first person in human history to discover an active volcano on another world. Sometimes I wonder if she felt the same awe and privilege that we feel now, knowing we're witnessing something no human eyes had ever seen before. Europa presented an even more tantalizing mystery. Beneath its icy surface, the Voyagers detected signs of what might be a subsurface ocean containing more water than all of Earth's oceans combined. This moon, smaller than our own, could harbor one of the solar system's most promising environments for life. The implications were staggering. If life could exist in Europa's dark oceans, it might also thrive in similar environments throughout the galaxy. Saturn revealed its own astounding secrets. What Earth-based telescopes saw as a few simple rings turned out to be thousands of individual ringlets, each with its own orbital dynamics. The Voyagers discovered that these rings are shepherded by tiny moons, creating gaps and waves in patterns so intricate they resemble cosmic clockwork. Some rings showed braided structures that seemed to defy the laws of physics, until careful analysis revealed the gravitational choreography of shepherd moons maintaining these impossible-seeming formations. The discovery of Enceladus at Saturn provided another potential habitat for life. This small icy moon shoots geysers of water ice hundreds of miles into space from its south polar region, fed by a subsurface ocean kept liquid by tidal heating. These geysers contain organic compounds and salts, suggesting a complex chemistry that could support living organisms. When Voyager 2 became the first and only spacecraft to visit Uranus in 1986, it encountered a world unlike anything we'd seen before. This ice giant rolls along its orbital path like a ball, with its axis of rotation tilted 98 degrees from vertical. Imagine Earth spinning on its side instead of upright. That's Uranus. This bizarre orientation means that each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness, as the planet completes its 84-year orbit around the Sun. The Voyager 2 flyby revealed Uranus's magnetic field to be tilted 59 degrees from its rotational axis and offset from the planet's center, a configuration so unusual that scientists initially thought their instruments were malfunctioning. The planet's moons showed signs of geological activity that shouldn't exist on such small, distant worlds. Miranda, in particular, displayed a surface that looked like it had been shattered and reassembled, with cliffs towering 12 miles high, more than twice the height of Mount Everest. Neptune, reached by Voyager 2 in 1989, proved even more surprising. This distant world, receiving only 1,000th the sunlight that Earth does, somehow generates winds exceeding 1,200 miles per hour, the fastest in the solar system. It's like discovering that the coldest, most remote place imaginable is also the windiest. These supersonic winds remain one of planetary science's great mysteries. How can a world so far from the sun's warmth generate such dynamic weather systems? Neptune's largest moon, Triton, provided the mission's final jaw-dropping revelation. This moon orbits backwards compared to Neptune's rotation, a clear sign that it's a captured Kuiper belt object, probably similar to Pluto. Despite being one of the coldest places in the solar system, with surface temperatures around -391 degrees Fahrenheit, Triton showed active nitrogen geysers erupting from its surface. It was like finding active volcanism on a world so cold that nitrogen, a gas at room temperature, exists as ice. The gravity assist technique that made this grand tour possible represents one of the most elegant applications of orbital mechanics ever conceived. As each spacecraft approached a planet, it essentially borrowed some of that world's orbital energy, accelerating to higher speeds without burning a drop of fuel. Jupiter accelerated Voyager 1 from about 38,000 to 52,000 miles per hour. Saturn added even more speed to both spacecraft. It's like catching a ride on a cosmic merry-go-round. If you time your approach just right, you can slingshot away at much higher speeds than when you arrived. The moment Voyager 1 crossed into interstellar space on August 25, 2012, humanity achieved something unprecedented in our species' history. For the first time, we had direct measurements from beyond our solar system's protective bubble. But determining exactly when this crossing occurred proved surprisingly challenging, requiring years of careful analysis and heated scientific debate. The boundary between our solar system and interstellar space isn't like crossing a line on a map. Instead, it's more like walking through a series of overlapping zones, each with its own unique characteristics. Scientists call this region the heliopause, but it's better thought of as a complex transition zone where solar wind particles gradually give way to the interstellar medium. Think of our solar system as a boat moving through cosmic waters. The sun creates a bow shock ahead of us as we plow through the interstellar medium at 60,000 miles per hour. Behind this bow shock, the solar wind creates a turbulent region called the heliosheath, where solar particles slow down and heat up as they encounter resistance from interstellar space. Finally, at the heliopause itself, solar particles can no longer push outward against the pressure of interstellar particles. Voyager 1's crossing revealed this boundary to be far more complex than anyone imagined. Instead of a sharp transition, the spacecraft encountered multiple zones with different properties. The magnetic field, cosmic ray intensity, and plasma properties all changed at different times and distances, creating a puzzle that took scientists years to solve. The key evidence came from Voyager's plasma wave instrument, which detected something entirely unexpected. The spacecraft could hear the cosmos itself. In the thin gas of interstellar space, plasma waves propagate like sound waves through air, creating what scientists call the cosmic hum, a continuous, low-frequency vibration that reveals the density and properties of the interstellar medium. Imagine being able to hear the universe itself breathing. That's essentially what this cosmic hum represents, the gentle vibration of interstellar space, like the soft resonance you might hear if you put your ear to a seashell, but instead of ocean waves, you're hearing the whispers of the galaxy itself. When Dr. Donald Gannett first heard these recordings, he said it was like listening to the voice of space itself for the first time. After decades of studying plasma waves, he finally had the privilege of hearing what the cosmos sounds like when no one else is around to listen. There's something deeply moving about that. We've given the universe its first voice. This cosmic hum tells us that the space between stars isn't the empty void we once imagined. Instead, it's more like a vast living organism, breathing and singing in frequencies our ears could never detect without help. We're not just exploring empty space, we're discovering that the universe is alive with subtle music, playing a song that's been going on for billions of years, waiting for someone to finally learn how to listen. When Voyager 2 crossed the heliopause in November 2018, it encountered conditions surprisingly different from those experienced by its twin. This wasn't supposed to happen. Both spacecraft should have entered similar regions of interstellar space. Instead, Voyager 2 found a denser, more turbulent environment, suggesting that the boundary between solar and interstellar space varies significantly in different directions. The space between stars, which the Voyagers now call home, represents one of the most extreme environments in the universe. The density is so low that if you could gather all the matter in a cube of space the size of Earth, it would weigh less than a paperclip. Yet this apparently empty void seethes with activity invisible to our senses. Interstellar space contains a thin soup of hydrogen and helium atoms, along with traces of heavier elements forged in the nuclear furnaces of ancient stars. The temperature of this gas hovers around 10,000 Kelvin, hot enough to vaporize any solid material, yet it feels cold because there are so few particles to transfer that heat. It's like being surrounded by a few million-degree particles that are spread so far apart they can't warm you up. Magnetic fields thread through this cosmic medium, creating invisible highways for charged particles. These galactic magnetic field lines, twisted by the rotation of our Milky Way galaxy, channel cosmic rays and plasma flows across distances measured in light years. The Voyagers have discovered that these magnetic structures are far more organized than anyone expected, creating what researchers call magnetic flux ropes, twisted bundles of field lines that act like cosmic cables carrying energy and particles between star systems. The cosmic rays permeating interstellar space represent some of the most energetic particles in the universe. These aren't really rays at all, but atomic nuclei accelerated to nearly the speed of light by supernova explosions, neutron star collisions, and other violent cosmic events. A single cosmic ray particle can carry more energy than a major league fastball concentrated into a space smaller than an atom, and each particle carries the memory of an ancient star that lived and died billions of years ago, their atoms now wandering peacefully through the galaxy like cosmic seeds on an endless wind. Within our solar system, the sun's magnetic field deflects most of these particles, creating what scientists call the cosmic ray shadow of our solar system. But the Voyager's measurements from interstellar space have revealed this shadow to have an unexpected shape, twisted and distorted by magnetic fields that don't match our theoretical models. Even more mysteriously, both spacecraft have detected cosmic ray particles flowing in organized streams, like invisible rivers in space. These cosmic ray highways appear to follow the galaxy's magnetic field lines, creating preferential paths for the most energetic particles in the universe. Understanding these flows could revolutionize our knowledge of how energy and matter move through the galaxy. The precision required to track and communicate with the Voyagers represents one of humanity's greatest technical achievements. Every piece of data we receive has traveled farther than any human-made signal in history, arriving at Earth with less power than a snowflake hitting the ground. NASA's Deep Space Network serves as humanity's cosmic telephone system, with massive radio dishes spread across 3 continents. These antennas, some as large as football fields, must track targets moving at 38,000 miles per hour across distances of 15 billion miles. The pointing accuracy required is equivalent to hitting a dime-sized target from 3,000 miles away. But catching the signal is only the beginning. The Voyagers transmit data at an agonizingly slow rate by modern standards, just 160 bits per second, about 300 times slower than a 1990s dial-up modem. A single digital photograph that your phone takes in an instant would require nearly 2 days to transmit from Voyager's current distance. Modern signal processing techniques have revolutionized how we extract information from these incredibly weak transmissions. Engineers have developed quantum-enhanced detection systems that can distinguish Voyager's faint voice from the electromagnetic noise generated by everything from cell phones to microwave ovens. These same techniques have found applications in medical imaging, astronomical observations, and even the search for extraterrestrial intelligence. The international collaboration supporting the Voyager mission spans the globe. When one Deep Space Network station loses contact due to Earth's rotation, another picks up the signal, ensuring we never lose touch with our distant ambassadors. European, Japanese, and Australian radio telescopes supplement NASA's network, creating a planetary web of cosmic ears. Machine learning algorithms now help scientists identify patterns in Voyager data that human observers might miss. These AI systems have revealed subtle rhythms in the cosmic ray flux that seem to correlate with our galaxy's rotation, hinting at large-scale structures in interstellar space that we're only beginning to understand. the engineering challenges of keeping 47-year-old spacecraft operational across interstellar distances would be impossible without the redundancy and reliability built into every Voyager system. Almost every critical component has a backup, and many systems have backups for their backups. When Voyager 2's primary radio transmitter failed in 1998, its backup system, which had been sitting dormant in space for 21 years, activated flawlessly and has operated perfectly ever since. This is equivalent to starting a car that's been parked outside for 2 decades and having it run like new. The spacecraft's attitude control systems use gyroscopes built in the 1970s that still maintain their orientation to within a fraction of a degree. These mechanical marvels spin at 19,200 revolutions per minute and have operated continuously for nearly half a century without maintenance, lubrication, or replacement. Software updates represent perhaps the most remarkable aspect of Voyager operations. Engineers have rewritten and uploaded entirely new programs dozens of times, essentially giving these spacecraft capabilities they were never designed to possess. It's like teaching a 1970s calculator to run modern smartphone applications, theoretically impossible, yet achieved through brilliant programming and creative engineering. The latest software updates include algorithms that can predict and compensate for component failures before they happen. When one of Voyager 1's thrusters showed signs of degradation in 2017, engineers activated a backup set that hadn't been used since 1980. These thrusters fired perfectly after 37 years of inactivity, demonstrating the incredible foresight of the original designers. Power management has become increasingly critical as the RTGs decay. Engineers have developed sophisticated protocols for sharing power between instruments, similar to how a smart electrical grid manages energy distribution during peak demand. Every milliwatt matters when you're operating the most distant human-made objects in existence. And here's something that gets me every time I think about it right now. Somewhere in the darkness between stars, these spacecraft are making decisions about which instruments to keep alive and which to let sleep forever. It's like watching an old friend slowly fade away, but knowing that every moment they're still with us is a gift beyond measure. There's something both heartbreaking and beautiful about that gentle decline, happening so far from home that we can barely imagine the loneliness. Even after nearly 5 decades of operation, the Voyagers continue to challenge our understanding of the universe in fundamental ways. Recent discoveries have revealed that interstellar space is far more dynamic and complex than anyone imagined. One of the most perplexing mysteries involves what scientists call anomalous cosmic rays, particles that don't quite fit our models of how cosmic radiation should behave. These particles appear to be accelerated by unknown mechanisms at the boundary of our solar system, gaining energy through processes that current physics struggles to explain. It's as if the edge of our solar system acts like a cosmic particle accelerator, boosting these particles to enormous energies through methods we don't understand. Both Voyagers have detected rhythmic variations in cosmic ray intensity that seem to follow patterns related to our galaxy's rotation. The Milky Way spins slowly, taking 225 million years to complete one rotation, yet somehow this galactic motion creates subtle beats in the cosmic radiation that the Voyagers can detect. These cosmic heartbeats might reflect large-scale structures in the galaxy that we've never directly observed. The discovery of interstellar tsunamis represents another frontier in our understanding. These are massive waves of charged particles that propagate through space at millions of miles per hour, carrying information about events that occurred hundreds of years ago in distant parts of our galaxy. Voyager 1 essentially receives cosmic mail that was posted before the founding of the United States. Magnetic reconnection events in interstellar space have revealed phenomena that challenge our understanding of plasma physics. When magnetic field lines in the interstellar medium suddenly snap and reconnect, they release enormous amounts of energy across vast distances. The Voyagers have detected these events occurring on scales previously thought impossible, suggesting that magnetic reconnection might be one of the galaxy's primary mechanisms for transferring energy. The Voyager missions have laid the groundwork for humanity's future exploration of interstellar space. Their discoveries are directly informing the design of next-generation missions that will follow in their cosmic footsteps. NASA's Interstellar Mapping and Acceleration Probe, launching in 2025, will create detailed maps of our solar system's boundary with unprecedented resolution. Using instruments thousands of times more sensitive than those aboard the Voyagers, IMAP will study how solar wind particles are accelerated at the heliopause and how cosmic rays from interstellar space penetrate our solar system. The European Space Agency's Comet Interceptor mission will study pristine visitors from interstellar space, providing ground truth for the conditions the Voyagers are measuring. These interstellar comets carry chemical signatures from other star systems, offering direct samples of the cosmic environment our spacecraft are exploring. Perhaps most ambitious is the Breakthrough Starshot initiative, which aims to send thousands of tiny spacecraft to Alpha Centauri at 20% the speed of light. These gram-scale probes would reach our nearest stellar neighbor in just 20 years, compared to the 70,000 years it would take the Voyagers to cover the same distance. The interstellar probe concept, currently in development by Johns Hopkins Applied Physics Laboratory, would travel 3 times faster than the Voyagers, reaching the heliopause in just 15 years and continuing into interstellar space with modern instruments. This mission would answer questions raised by the Voyagers while pushing the boundaries of human exploration even further. Advanced propulsion technologies under development could revolutionize interstellar exploration. Fusion rockets, solar sails, and antimatter engines could accelerate future spacecraft to significant fractions of light speed, making detailed studies of nearby star systems possible within human lifetimes. The Voyager missions have fundamentally transformed our understanding of planetary science, heliophysics, and our place in the galaxy. They've revealed that our solar system is far more dynamic and complex than anyone imagined when they launched. Their discovery of active geology on moons throughout the outer solar system revolutionized our understanding of where life might exist. Europa, Enceladus, and Titan now rank among the most promising targets in the search for extraterrestrial life, their subsurface oceans potentially harboring the ingredients for biological processes. The missions have also challenged our understanding of planetary formation and evolution. The bizarre tilts and magnetic fields of Uranus and Neptune suggest violent collisions in the early solar system. The backward orbit of Triton and the tilted rotation of Uranus hint at a chaotic period when large objects regularly crashed into the forming planets. In the realm of heliophysics, the Voyagers have revealed our solar system's interaction with the galaxy to be far more complex than theoretical models predicted. The shape of the heliosphere, the properties of the heliopause, and the behavior of cosmic rays all differ significantly from pre-Voyager expectations. These discoveries have implications that extend far beyond our solar system. If magnetic structures and particle flows like those detected by the Voyagers exist throughout the galaxy, they could fundamentally change our understanding of stellar evolution, planet formation, and the potential for life around other stars. The technologies developed for the Voyager missions have found applications far beyond space exploration. The ultra-sensitive receivers designed to catch their faint signals have improved medical imaging systems, radio astronomy, and telecommunications. The power management techniques pioneered for the Voyagers have influenced everything from satellite design to electric vehicle batteries. The methods for extracting maximum efficiency from declining power sources have applications in renewable energy systems and remote sensing equipment. Navigation techniques developed for tracking the Voyagers across interstellar distances have improved GPS accuracy and enabled precision landing systems for spacecraft. The mathematical models used to predict their trajectories have found applications in asteroid tracking and planetary defense systems. The redundancy and reliability engineering that keeps the Voyagers operating after 47 years has influenced the design of everything from medical devices to autonomous vehicles. The philosophy of building systems that gracefully degrade rather than catastrophically fail has become standard practice in critical applications. As we contemplate the Voyager's journey, we're confronted with profound questions about time, space, and humanity's place in the cosmos. These spacecraft represent our species' first serious attempt to become a spacefaring civilization, to extend our presence beyond our home planet in a meaningful way. The golden records aboard each Voyager contain sounds and images selected to represent the diversity of life and culture on Earth. But they also reflect the optimism and ambition of the people who created them. In 1977, when the records were assembled, the world was divided by the Cold War, yet scientists from many nations contributed to this cosmic greeting card. The records will likely outlast every human artifact on Earth. Billions of years from now, when our sun has expanded into a red giant and consumed our planet, when all evidence of human civilization has been erased, the Voyagers will still carry our voices through the galaxy. They're our most lasting legacy, a testament to human curiosity and ingenuity that will persist long after our species has either evolved into something unrecognizable or vanished entirely. What's remarkable is how the Voyagers have changed our perspective on Earth itself. The famous pale blue dot photograph, taken by Voyager 1 from 4 billion miles away, shows our entire world as a tiny speck of light suspended in a sunbeam. Carl Sagan's reflection on this image remains one of the most moving pieces of science writing ever composed, reminding us that everyone we've ever known, every human drama that has ever unfolded, has taken place on that tiny mote of dust. The Voyagers teach us about the value of long-term thinking. In an age of quarterly reports and election cycles, these missions remind us what we can accomplish when we commit to projects that span decades. The scientists who designed the Voyagers knew they might not live to see their greatest discoveries, yet they built them anyway, as gifts to future generations and to the sum of human knowledge. As we reach the end of our journey through the remarkable story of the Voyager twins, it's worth taking a moment to appreciate what these missions truly represent. These are not just spacecraft, they're humanity's first serious attempt to touch the stars, to extend our consciousness beyond the confines of our solar system. Right now, as you're listening to these words, both Voyagers continue their eternal journey through the galaxy. Every second, they travel about 11 miles farther from home, pushing deeper into realms that no human has ever directly observed. Their nuclear hearts, steadily beating since the Carter administration, still power instruments that continue to make discoveries about the nature of interstellar space. The engineering achievement they represent is staggering. Built with technology from an era when computers filled rooms and mobile phones were science fiction, these spacecraft have operated flawlessly for nearly half a century in the most hostile environment imaginable. They've survived cosmic ray bombardment, temperature extremes that would shatter most materials, and the slow decay of their own power sources. But beyond their technological triumph, the Voyagers represent something deeper about human nature. They embody our irrepressible curiosity, our refusal to accept boundaries, our determination to explore and understand regardless of the cost or difficulty. In an age when we often seem divided by differences, the Voyagers remind us of what we can accomplish when we work together toward a common goal. The scientific discoveries they've enabled have rewritten textbooks and challenged our most fundamental assumptions about how the universe works. They've revealed the outer solar system to be a realm of incredible diversity and beauty, shown us that the space between stars is far from empty, and provided our first direct measurements from beyond our cosmic home. Looking ahead, the Voyagers still have stories to tell. Their power will gradually fade over the next decade, and one by one their instruments will fall silent. But their journey will continue for millions of years, carrying our golden records through the galaxy long after Earth itself has ceased to exist. Perhaps most remarkably, the Voyagers have shown us that the universe is knowable. Through careful observation, clever engineering, and patient analysis, we can understand phenomena occurring billions of miles away. We can trace the behavior of particles accelerated by stellar explosions, map magnetic fields that span light years, and measure the temperature of space itself. The next time you step outside on a clear night and look up at the stars, remember that somewhere out there, two tiny spacecraft built by human hands are carrying our voices into the cosmic dark. They're proof that we can transcend our earthly limitations, that despite our brief lifespans and fragile bodies, we can create things that endure across cosmic time. The Voyagers are humanity's greatest love letter to the universe, a declaration that we were here, we wondered, we explored, and we refused to accept that anything was beyond our reach. They remind us that even in our darkest moments we're capable of achievements that illuminate the cosmos itself. Before you drift off to sleep tonight, I'd love to hear your thoughts in the comments below. What fascinates you most about the Voyager mission? Is it the incredible distances they've traveled, the golden records carrying our voices to the stars, the scientific discoveries that have rewritten our understanding of the cosmos, or perhaps the simple fact that these spacecraft will outlive our entire civilization? Share what captures your imagination about these cosmic messengers. Thank you for joining me on this inaugural voyage into the cosmos. If you'd like these nighttime journeys to the stars to continue, please subscribe and help our Night Voyager community grow. Until we meet again in the cosmic dark, fellow Voyagers, may your dreams carry you to distant worlds.